Thank you very much. I'm actually impressed that you found out everything about my bio. I didn't expect this to happen. In particular, there's one thing that I wanted to highlight about my bio here, which is the fact that it is typically not, well, it's not that typical to do this bike tour by idea of neuroscience. And the reason why I actually did this was, I think we can ignore the legal information, please read it, but we can directly go on. But the reason for me to do a year in neuroscience is that I'm astounded by one specific skill of the human brain that I wanted to understand at least a bit. And this is actually to perform skillful movements. Afterwards, I moved on, not directly to the TU Munich, but to the German Aerospace Center, where I actually did most of my work, in order to do work in robotics and artificial intelligence. And if you've ever worked in a robotics lab or you saw the demos by the robotics labs, you will notice that, according to the videos, we came quite close in actually mimicking this whole skillful movement set. Well, if you've ever worked at a robotics lab, you notice that those are the videos that are being published. My daily work typically looked more like this. This is a finding, an interesting finding that is typically summarized in Moravec's paradoxon, which states that typically it's quite easy for computers to perform skills which are hard for humans, or it's quite easy for humans to perform skills which are hard for computers, or the other way around. Ever since 1997, we've got computers that are substantially better than the best chess players, which is a really difficult logical task. But up to now, we don't actually have, we don't actually have a robot that can perform a movement of a chess figure with the same dexterity as a small child. And that's despite the fact that our brain actually just weighs 1.4 kilograms, substantially less than our supercomputers, and consumes a fraction of the power of my laptop here. One of the reasons why this is the case is that actually the computers, the processors that we find at companies like Intel, NVIDIA, AMD, and so on, think very differently from the way how our brain performs. And in neuromorphic computing, we're trying to build the next generation of processors and software that closes this gap to also become good at what humans are good at. In the next roughly 20 minutes, I want to give you an overview of what neuromorphic computing means and what neuromorphic computing hardware is, using the example of Intel's Loihi 2 chip. Afterwards, the animations are gone, sorry for that. Afterwards, but the animations did work before, didn't they? Yeah. Great. Please stop me if the animations don't work. Afterwards, I want to give you an introduction about why neuromorphic hardware applies a different kind of neural network called spiking neural networks, how to train spiking neural networks, and in the end, I want to give you a rough overview of some examples of where we found Loihi neuromorphic computing and spiking neural networks to perform really well. Afterwards, my colleague Alessandro will give you an overview of how you can run your own spiking neural networks and translate your applications into the neuromorphic domain. So there's one thing that I should mention first of all. This is mostly about one specific neuromorphic processor, the Intel Loihi 2 processor for, well, obvious reasons given where my paycheck comes from. Though there's a huge variety of neuromorphic computing in the field based on the question of how closely do I want to mimic what's actually going on in the brain in silicon. We took the approach to say that we are basing our hardware on the fact of sparse asynchronous computing. What does this mean? Well, let's look at a typical common processors nowadays with high parallelism, like a GPU, where we've got lots and lots of cores. And typically we've got a central clock. And this central clock tells all of those cores to perform a computation now, and now, and now, and now. And that means all of those cores will perform a computation and will send in information further. That's pretty good if you want to have highly dense computation. But in many real-world computations, what you actually notice is that you've got sparse information, you've got sparse computation. It means in many time steps, many of those processors actually don't need to compute anything. the signal doesn't have changed because we're looking at a video stream where the pixels don't change that much from one frame to the next. And therefore, what happens in those cases is that many of those cores will just perform the same computation that they already did, or perform no computation at all, and they will output just lots and lots of zeros. In Loihi, we got rid of the central clock. Instead, we basically let all processes run at the speed that they need, and if they don't need to perform anything, we just leave them silent. That means, first of all, we can leave them idle, meaning we can save energy. It also means that we can substantially save bandwidth in some applications. This whole idea comes from a startup that Intel acquired in 2011, which was working on Ethernet switches. The point being that also in Ethernet and Internet applications, you've got several computers all working at their own pace that you somehow need to enable communication between. Now, I mentioned that this leads to a different architecture. And this was the fundamental principle that we based our chip on. But it led to quite a few design decisions that followed from it. And all of those design decisions kind of led us further down the rabbit hole towards more and more brain-like architectures, which I find was quite an interesting finding. One of the next things was the question of what do we do with memory? Typically, in most conventional processors, you've got a separation between the compute and the memory, which is good if you want to have like a big chunk of memory. And that works pretty well. If you know that you've got like 500 processors, cores, and in each time step you need 500 scalar values or anything like this, you can know that you need to read in those 500 scalar values from memory, read it in, and you know that you will get 500 scalar values back and you can pre-allocate this memory. Works pretty well. Doesn't work well if you don't really know how much information you will get in return. That means in this case, we couldn't really live with this phenomenon bottleneck anymore, and instead we had to integrate the compute into the memory. This has one disadvantage. If we compute it directly into the silicon, well, the most expensive thing in the semiconductor industry is silicon. That means if we integrate the memory into the silicon, that means we need more silicon, being more expensive, and we don't want to have big memory. That means if you are looking for anything like you've got a big database of things stored like MNIS or a bigger database, Cocos, stored somewhere on external memory, which is cheap, want to quickly read into a chip and out of the chip, won't work with neuromorphic hardware. However, it has a good advantage. It means that each core will have its tiny memory integrated into the silicon. And as long as you need to perform some iterative calculations on this memory, you are really quick, you are really fast and energy efficient because you're fully eliminating the phenomenon bottleneck. As mentioned, then we've also got this point of very parallel computing. Basically, since each core has its own tiny memory, you can arbitrarily scale. You don't need to consider, well, now I've got twice as many twice as many cores. If I need to somehow align them with the memory, each core can just do whatever it wants, and therefore you can easily scale to big parallel systems. And since you've got memory pretty close to the cores, you can easily also just iteratively update parameters of the neural network, like synaptic weights, based on some information stored in those cores. So, why does this lead to a different kind of neural network? Let's briefly recap what a neural network in computer science typically looks like. In artificial neural networks, you typically have neurons that in each time step receive some information, scalar values, perform a function on it, like a rectifying linear unit, and then provide some output in each time step. We mentioned that neuromorphic hardware, in particular Loihi 2, is typically optimized for event-based sparse coding. That means you message only when needed. This is, as mentioned, quite interesting if you've got any temporal continuity, like in videos, where each pixel, doesn't really change that much. It also means that we are typically trying to look at networks which have a sparse connectivity structure. In artificial neural networks like nowadays transformers, you've got a very dense connectivity between layers. In neuromorphic computing, you rather want to look at sparse computation. The reason being, if you've got lots and lots of input to each neuron, the chances are high that it will receive some information. It needs to perform some computations in each time step, and then it becomes inefficient. Instead, what you want to do is you want to have rather sparse connectivity so that you can ensure that in many time steps you won't get any input. And that means those processes are typically applied with some acceleration for unstructured or structured sparsity, like convolution, like random stochastic connectivity, or anything like. Next thing, and this is where I think it becomes really interesting, is the idea of state for neurons. As mentioned, each pore, each neuron has its own tiny memory. In artificial neural networks, each neuron just performs a calculation and forgets everything it has ever stored. Here, in spiking neural networks, we've got a tiny, tiny memory. This has one disadvantage, as mentioned. We need more silicon. The more neurons we've got, the more silicon we need, the more expensive the chip becomes. But it means that if we've got temporal redundancy, the neuron can just maintain its state, just say, okay, I know already what I should have computed, and therefore I can save operations. And it also allows neuron dynamics. It means we can iteratively update and quickly and energy efficiently update the states of the neurons to show some dynamics. That means basically now we are going from a typical feed-forward network to actual dynamic systems encoded in hardware. And later on, when we're looking at the applications, I'll give you some glimpse into why this has, in some cases, crucial benefits. Next point is that this is typically optimized and pretty good for our recurrent networks. In recurrent networks, you've got further advantages. You've got the advantage that typically the next time step depends on the last time step. And that means you've got an advantage of actually storing the state over some time steps. And therefore, in order to reuse those states, but they've got some cons, which is, depending on the neural network, it's hard to train. And the last thing, the last property of spiking neural networks is typically that you've got delays as a computational unit. This stems from the fact that you've got sparse messaging. Therefore, it doesn't really cost you too much memory to just delay individual pieces of the message by a few time steps. And therefore, you can have your own tiny memory, basically a short time memory, and store each message for those time steps. This has quite some important tasks for, well, temporal processing, audio processing, video processing, and so on. Okay, so we've got this range of properties of spiking neural networks stemming from how the hardware actually works if we've got asynchronous compute and memory processing. How do we actually encode information? This is something where spiking neural networks gets a bit more intricate, but also a bit more powerful, because other than in artificial neural networks, I think you've got substantially more opportunities to actually encode information, but it also means you have to explore what encoding actually works for your application. The first one is to actually encode things as precise patterns. Let's assume I've got spikes at one time step and then 10 time steps later and also 5 time steps later. And this is something that, depending on the network, we could interpret it as, well, this picture actually shows us a cat. We could look at the rate of spikes. That means if we've got spikes coming in at like 5 Hertz, this could imply that it's a cat. 10 Hertz could imply that it's a dog. The spiking intervals between spikes. Now we are really talking about the temporal precise coding. The phase of spikes, and one thing that I will come to in the, well, rather end of my talk is delta spikes, so that I'm not signaling each signal. The neuron currently has a state of 5, and I'm not signaling the state of the neuron, but I'm just signaling changes. Only if the neuronal state has jumped from 5 to 8, I will signal a 3. Okay, how do I train the network? Well, the answer, first of all, is simple. Because, well, when I got invited for this talk by Marcel, he asked me this question of how can I have my artificial neural network and translate into a spiking neural network. I mean, that's basically what we want to do at AutoML. We want to make it as easy as possible to go from one architecture to the next to figure out if the next might be more efficient. And after our group has been working on this spiking neural network thing for like 6 years, I think there's a pretty clear answer to how to do this translation. Don't. It's typically not really that efficient. That means what you typically want to do is you have to retrain your network. There are some ways how you can actually translate artificial neural networks to spiking neural networks. If you want to go through this, I can give you some slides on this later on. But typically, if you want to become really performant, if you really want to use neuromorphic computing and show all performance of using the features of neuromorphic hardware, you want to train it from scratch. And that means typically you can apply simple backpropagation. However, there are two differences to artificial neural networks, and this is where you need a different kind of backpropagation. The first is you've got temporal dynamics. Unlike artificial neural networks, each neuron has some temporal dynamics, and you somehow need to take care of this once you're propagating the error back through the network. And the second is delta functions. They destroy quite a lot in many applications in computational neuroscience. In artificial neural networks, you've got changes in signals, and you can interpret those changes in signals as errors, or you can say, yeah, if I change the input by so much, it will just slightly change my output. In spiking neural networks, the change often means either I get a spike or I don't get a spike, and that's one thing where you can hardly calculate a gradient. So the answer, and this is one thing that mostly comes from one of my colleagues, Sumit, pretty smart guy. First of all, the temporal dynamics are not that much of a problem, because what you can do is you can just use, in order to calculate how the gradient is being transformed through temporal dynamics, you can use a temporally inverse system. That means if you've got such a dynamics in the forward path as showing on the left-hand side, you can calculate the inverse dynamics and use that in order to propagate the error back through time. Similarly, if you've got a delay in the forward path of your network, your inference path means that you can just use an advanced step in the error back propagation path. And for the delta functions, we're using a trick that was also briefly mentioned yesterday. We relax the function. That's something that is being called surrogate gradients nowadays. And that basically means you're not looking at the actual time step. You're not assuming for error back propagation that you actually have a spike. You're relaxing it using different functions to calculate a surrogate gradient. And then the limit and some limits, this function actually approaches this delta step function. Okay, so quite a few years ago, Intel has developed its first chip, its first Loihi 1 chip. It has developed how we can, together with the whole community, it's a big community, it's far from just from Intel, just Intel. We have developed so many things of how you could encode information, how you could train networks. It raises the question of what is it actually good for? And that's a question which typically is being asked very early in industrial research, and I'm quite happy that in our case this was not asked very early, first of all. So that first of all, Intel was able to develop chips, to develop infrastructure and so on, and then try to figure out what can we actually use this cool technology for. And that's one thing that is typically being done best in a big community effort. That means at this point, Intel started the Intel Neuromorphic Research Community. That means if you're interested, I also show you links later on, if you're interested to run things actually on Loihi, you can apply to become a member of this community, like I think 200 other companies, research institutes nowadays, and we'll provide you with access to it so that you can just try out what it works well with. Just play around with it on our clusters, or if you need some hardware, we can provide you also with the hardware. We give you some training, either at workshops like this, or at some workshops that we are also organizing ourselves. And then we're trying to help you get up to speed and show where Loihi can actually be used. And up to end of 2021, this is what the community reported to us. By now there are more data points, but we just didn't find the time to summarize them. And I think there are quite a few interesting aspects in this graph that I want to highlight. The first thing are the metrics that the community typically found out to work quite well. First metric, I hope you can read it. Sorry, it's a bit tiny. The first metric is the energy ratio. That means how much more energy efficient is it to perform any of those tasks. Each dot represents one specific task, like SLAM. And how much more energy efficient is running it on Loihi in comparison to any conventional hardware like CPUs, GPUs, AI accelerators, and so on. The second metric, and that's one metric that I think wasn't mentioned here before for neuromorphic computing, is the speed solution, the latency, like how quickly can I input a problem and get the output back. And here we typically use the ratio, meaning how much faster is Loihi, how much more energy efficient is Loihi in comparison to conventional hardware, or how much faster is it in comparison to conventional hardware. And there are actually lots of tasks where Loihi just fails. That means Loihi is less energy efficient, slower than conventional hardware, and that means those are tasks where you wouldn't apply Loihi for, where you definitely would not develop a new hardware for. And then again, there are those tasks here on the top right-hand corner, where Loihi actually does show out performance. In some cases, some astonishing performance of, well, 1000x more energy efficient, more than 100x faster. And I will pick two example applications. Strange, something really went wrong with the animation.
Sorry, can I add something with me?
Absolutely, sure.
It goes back this slide. Can you tell us more about the hardware you had now as reference architecture, CPU, GPUs, more videos? I don't know, that was not. How is that impacting your picture?
Oh, sorry. Basically, you see here, if you're looking at different tasks, we always, well, the community use one task, like for example, I think this one is graph search, breadth first graph search, to figure out is it more performant than a specific conventional hardware that this task is currently typically being run on. That means they're looking at, well, if you've got a circle, it's in comparison to CPU.
It's a comparison to that. Okay, I missed that part. Okay.
Oh, sorry, I should have mentioned. Yeah, thanks for the clarification question. Sure, go ahead.
For the parity line, why doesn't it go through one consistent ratio, right? So it could be
I think it goes through one.
I mean the dash line.
Oh, yeah. That's one thing that where we typically say, in the end, we compare something that is called the energy delay product. It means if we want to figure out, is it better than conventional hardware, we multiply the gain obtained from the energy times the gain from the solution. And only if this product is better than, is higher than one, then we claim that we're better. The reason being that in parallel hardware, particularly in scalable hardware, you can typically trade off energy with time. To give an example, what we can do is we can say maybe running a neural network shows less accuracy than on conventional hardware, or is slower than on conventional hardware. What we can do with scalable hardware, we can just use twice as many resources, twice as many cores in order to speed things up.
Okay.
And using twice as many cores will mean that we've got a decrease in energy performance, but an increase in time performance. And therefore, you can easily tweak those numbers by saying, yeah, if I put enough energy into it, I can easily just increase my performance. Or similarly, one thing that works quite well for neuromorphic hardware is that it often operates at low voltages. Low voltages meaning less hertz, slower, but higher energy efficiency. And that's one thing where just by changing the voltage in CPUs, GPUs, you can gain a lot of performance, time performance, while sacrificing energy. And therefore, it's unfair to say, yeah, we're faster than something, but we're ignoring the energy performance. Typically, you want to use both values, and therefore we're typically reporting all performances or underperformances using the energy delay product. Awesome. Thanks for the question. pretty strange what the animation do. Anyway, out of those range of applications that I just showed you, there are two that I want to pick out. And the first one I want to pick out because it was actually quite surprising for us. Initially, we developed the into one chip with the goal of, well, it's neural networks, but of course we should go for deep learning or anything like this. But it turned out that one of the best performing operations was actually mathematical optimization. And let me give you an example of why this is actually the case. Oh, actually, I noticed why this is not, the animations are not working. Let me just quickly change that. Because this is the animation that I used in order to create the PDF yesterday evening. If I remove many of the animations. Yeah, now it works. Awesome. That was a quick fix. So the first thing the first example of where Loihi 2 and neuromorphic computing performs quite well, they want to go into is optimization. And therefore, let me give you one example. The example of quadratic, unconstrained binary optimization. Or let's just shorten it to QUBO, otherwise I can't pronounce it more than twice. And that's one thing that I just want to focus on because we just recently published a solver for Loihi 2 on our GitHub repo. The good thing about QUBO is it's quite straightforward to explain what it is. The name basically gives it away. We've got a quadratic cost function. We've got no constraints. We've got binary values. That means x can take 0 or 1. And we want to optimize the cost function. We can look at one specific example. Let's look at this example QUBO matrix. And what we can do is we can encode the variables, those 0 or 1 binary variables, as state of the network. And that's the first thing where we differentiate from artificial neural networks. As mentioned, all neurons have states that can be used in order to encode variables over time. Second point, we can then use the synapses to represent the entries of the QUBO matrix. And now what happens if one of the neurons actually decides to switch one of its states? We can send a spike, an event, via the synapses, and update all of the connected neurons about this information so that those connected neurons can use this new information. Actually, I'm connected with one maybe conflicting neuron in order to figure out whether they should update their states as well. And then we can use the dynamics of the neurons that can build into the neurons in order to iteratively find an optimal solution. In our case, it's simulated annealing. That means initially we still put lots of noise into the network to roughly raster the whole space to figure out where are areas that are worth exploring before we iteratively go down the gradient to find the hopefully global solution. Why is this performant on neuromorphic hardware? First of all, because we've got massive fine granular parallelism. That means we can simultaneously check for all variables where they should be updated, and we can in parallel compute all contributions from all variables to the overall cost. That means we can quickly just monitor the cost. Next point is we've got compute in memory integration. That means it's pretty quick and efficient to iteratively update those variables. And we've got asynchronous computing and communication, which means that in the end, when we are slowly converging and only need to change very few variables over time, we can just leave most of the massively parallel cores idle, therefore saving energy, saving bandwidth, and therefore time. And we're working with a few partners, in particular here from industry, to figure out where you can use the specific kind of optimization. Really, there's a big pull behind the specific QUBO task because D-Wave, a quantum computing company, claims to be able to solve this as well. And I want to highlight this specific task mainly because space is cool. This is a task of, we've got some satellites flying around the Earth orbit, and we need to decide on their viewing angles so that we can cover as many of those areas that we want to observe as possible. And one thing that you can see here is that we are, our current solver, a factor of roughly 10x faster and 250x lower energy, more energy efficient, which is particularly important if your whole source of energy is the sun and solar panels, and you don't want to waste too much energy on computation. And the next thing that I want to go into is deep learning. This time not because it's that much surprising, but because in industry, it's kind of the bread and butter. If you're going anywhere and saying, yeah, I've got a new chip for neural networks, everyone will ask, how does it perform on deep learning? And up to the second version of Loihi 2, it didn't really perform that well. That means many of the points that you saw in the initial picture on the lower left-hand side were actually deep learning applications, and that changed mainly with Loihi 2. The reason being is that it encodes something that we use as, that we define as sigma delta networks. That means we're looking, for example, at a video stream, and we're looking at many, many pixels, and most of those pixels don't change over time. Therefore, what we can do now with Loihi 2 is we can actually calculate only the difference, the changes of those pixels, and we can communicate only those changes in pixels. That means all of those neurons that don't have any news will just stay idle and won't consume any power consumption. This, in some applications that we went through, typically reduces the amount of computation that need to be performed by a factor of roughly 10x. And if you're looking at some applications, this will be one from the video domain, which is called a pilot net, where we've got a video stream with slowly varying pixels, and we want to predict, for example, here the steering wheel angle. And one thing that we found out, this is pretty new results from the summit I just mentioned. Therefore, this is not really fine-tuned yet. This was just something of, let's try it out. Therefore, still quite hot. At the moment here, this network is slightly less accurate. A factor, sorry, you probably can't read the green letters as well here. A factor of 2.x faster latency, a 25x higher throughput. And one thing that you notice quite commonly in neuromorphic hardware, the energy efficiency is typically the biggest gain. Here we are more efficient by a factor of roughly 150x in comparison to an NVIDIA Jetson or a Nano, I think it is. That means the GPU that NVIDIA builds in particular for embedded systems. That means that those are optimized for systems that run on battery, basically. Similarly, for audio denoising, this was a challenge that we gave out, where we basically just asked the community of, well, can you show us how we can optimally denoise audio? And we'll give you a prize if you can do it quite well. Task is basically that you're using Teams, you're speaking into the microphone, and maybe in the background you've got children screaming, you've got cars running around, you've got trains, anything like that, and you want to denoisify it. And that's a task where typically processors have some specific accelerators inbuilt, which need to be energy efficient because, well, the laptop should have a long battery life. And this is one thing, sorry, once again, you probably will have a hard time reading the green letters. Here the latency is, once again, those were our initially baseline results. Those are not the results from the community yet. Here's slightly slower latency. Interestingly, our networks are even have a higher accuracy, but I would say it's roughly on par. But in particular, the energy efficiency here is a factor of 74x. That means substantially more energy efficient. And with those words, I want to come over to an end with my presentation. Though there will be an additional point that I will lead into next. But first of all, one thing that I want to mention here is this has to raise the interest. If you think that maybe neuromorphic computing, Loihi 2, can solve some of the problems that you're interested in, can solve some of the applications you're interested in, the first thing to do is go on to our GitHub repos, clone it, and try to write your own spiking neural networks. And Alessandro will, in a minute, show you how this is actually being done. In order to then run it on Loihi 2, we need to slightly restrict the access, apply to become a member of Interest Neuromorphic Research Community. And if you're interested to go fully into this project, in this problem, in this whole domain, please look at our website. There are typically often jobs that are being announced and look for those, or of course, please always feel free to reach out to us. And with those words, I want to thank you for your attention.